Welcome to Easy Mathematics and a new video. Today's topic is awesome sums. Little wordplay. We talk about mysterious series and its triggy origin. Of course, of the word triggy, you know what is going on. It involves trigonometric functions. And what we want to do, we want to discuss or talk about some crazy looking sums like this. You can see, and if you see such crazy identities, then the name Ramanujan is not far away. As you know, what I want to say first is, before we start the video, this sum from Ramanujan we will not discuss in detail in this video. This should be a complete own video. I just want to mention it. We discuss similar versions of this, okay? Similar looking sums, I should say. Okay, so first I want to give an overview, then we take a look of some examples, then we discuss the basics, and we will see, or I want to let you know that this video I will not go through all the details. They are very easy. I just want to give an overview about such summations, how to derive them, how to find them, and I leave the most of the details I will leave up to you. Okay, good. So what we want to do, we wanna discuss such sums you have seen above, and series involving in particular the inverse tangent functions, and we will do this in 2 or 3 videos, I do not know yet. And our goal is to understand where those crazy looking identities come from, and what you should be familiar with differentiating hyperbolic functions, complex numbers, and basic properties. And what we will see is that some of those identities, we will see, they look crazy, but if you understand how to derive them, then it looks not so complicated. And Ramanujan and others, they had this idea, and they followed it. And as you can guess, Ramanujan had more than one good idea. In particular, it needs much more to derive his crazy formula. So therefore, an important question: will we prove Ramanujan's sum? Not in this video. Like I said, this should be an own video, but we discuss a similar sum you can see here. Okay, we will discuss where it comes from and how to evaluate it. It looks really crazy, and just for comparison reason, you see that they look quite similar. The second sum is from Ramanujan, and like I said, we will prove it in another video. This is not so easy in some sense like the version above. This is more easy to understand if we have some basics. Okay? Yes, so I give some examples just to get an idea. The first summation, it looks quite ordinary, nothing special, and there is a more general form. This is, you can see here. I will not read the complete sum, of course. You can see it by yourself. It doesn't make sense you to read all the terms. But I want to say, if you put a equals 0, you get this sum. Okay, so this one is a special case of this sum. And where does this crazy sum come from? It comes from a summation over inverse tangents, and then when you differentiate both sides with respect to a, then you get this summation here. Okay, so if you are familiar with differentiating, please make sure to derive the derivative and compare it to this one. Okay, yeah, and of course we can play the game again. So the equation 5 we can differentiate again with respect to a to get this crazy looking summation. Yeah, and then we can discuss also special cases like a equals 1. Okay, you can do it by yourself. Though very important is many of those crazy identities, they come from differentiating some expression with respect to a variable. Okay, this is what you should take with you. Okay, another nice example is this summation. Maybe we prove it, I do not know yet, just want to show you. It looks very nice. It's a summation of some cosines and hyperbolic sines and hyperbolic cosines and so on, and yeah, it has a closed form. Here you can see it. Okay, but we will take care of these inverse tangents, how to find those identities involving inverse tangent, and it's not so complicated. It's just a beautiful idea, and it's more or less an obvious idea, more or less. First, you should know the addition formula for the inverse tangent. Here you can see it. The proof is simple and it's also well known. If you want to see details, please look by yourself. It's not so hard. We will not discuss the details here, okay? And we make an observation in general for finite sums. If we have a finite sum S of n, the summation over ak from k equals 1 to n, we can make summation trivial if we can find bk such that ak equals bk minus 1 for all k. Then S of n is bn minus b0. This is what we call telescoping sum or telescoping property. Okay. And then for infinite sums we take the limit. Okay, so the infinite sum is the limit of the finite sum as n approaches infinity. Okay. Yeah, so telescoping property, this is the main keyword for this video, and yeah, to evaluate sums involving inverse tangents, we choose h of k carefully to take advantage of the telescoping property. Okay, and a natural choice for h of k is what? Based on the addition formula, of course, this one. Please make sure that you see why it's a natural choice, and if you plug in h of k here in this summation and make use of the telescoping property, we see that the summation from k equals 1 to n over inverse tangents of h of k is the inverse tangent of f of n plus 1 minus inverse tangent of f of 1. Okay? This follows immediately by the addition formula for the inverse tangent. Okay? So now we have a powerful setup we can choose different f of k's, and if we choose it more carefully, so in particular, if f has a specific property, then we have no integer multiple of pi. Yeah, so the general case of the summation is that the summation of the inverse tangent using the telescoping property, there is also integer multiple of pi for 1L. Here L is 0, and L is 0 because f has a specific property. You can think about it. And exercise 1, prove that L is given by this expression, the summation, when n over the sine of f of k, whenever fk times fk plus 1 is smaller 1. Alright, so it has to do with the addition formula for the inverse tangent, of course. You can think about that. Then if you see here this property, then it should be clear what specific property makes here the integer value L equals 0. Great. So, what now? We consider different f of k's, then we get an h of k, then we make use of the telescoping property, and we get s of n, and then we are happy. Okay, and we consider in particular f of k is ak plus b, where a and b are such that f of k is greater 0, greater or equal 0, for k greater 1, and we discuss f of k quadratic, where the discriminant is less or equal to 0. And then we can think of telescoping twice or even more. Yeah, and we discuss the cases f of k is k and f of k is minus a over k squared plus 1. Okay, so let's do it. F of k, ak plus b. If we plug in ak plus b for f of k in h of k, you get h of k is a over the quadratic polynomial in k. Okay, so then using the telescoping property, because this is the addition formula for the inverse tangent, yeah, you can plug in all this stuff carefully, and we see that inverse tangent of a over a squared k squared plus blah 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 is inverse tangent pi over 2 minus inverse tangent a plus b. Nice. And so this summation, it looks so crazy, but the result is in so beautiful form, and we see that we only make usage of the telescoping property using the addition formula for the inverse tangent to get some nice summations. Now we can discuss special cases, for example a equals 1, b equals 0, or a equals 2 and b equals 0, and we get these two summations. Alright. Now this sum we can differentiate with respect to a, and we can set a equals 1, b equals 0, and for example a 1 over 2 and b 1 over 3 to get these two identities. They look also really nice. A quadratic polynomial over a quartic polynomial, also here with some crazy looking coefficients. Yeah, the summation results in nice values like 1 over 2 or 1 over 61. If we take f of k quadratic, then h of k looks like this: 2ax plus a plus b over a polynomial in x of degree 4. Yeah, this is not x, of course, it should be k. Pardon, we change it. So I've corrected it. Polynomial in k of degree 4. There are some coefficients a4 to up to a0, and exercise 2, as you can guess, determine the coefficients. I do not want to write them here because it gets really messy, and yeah, you can take care of the coefficients. It's not so important. If you want the details, please do it by yourself. It's not so difficult. Then of course we can discuss special cases. For example, b equals minus a and z is a over 2 to get this nice sum, and the other special case b equals minus a and c equals 0 to get here the second summation. I want to point out that the second sum is independent from a, so the right hand side. Here the right hand side is depending on a, here it's not. This is, it's a nice observation, I guess. And again, I want to say that if you see these summations for the first time, they look so crazy, and you can say, what on earth is going on here? Who the heck found it? How to come up with this? And all we do is we take advantage of the telescoping property, and this makes the summation very easy, and we have a great tool to derive a couple of beautiful summations. For example, telescoping twice. If we consider h of k is f of k plus 1 minus f of k minus 1 over 1 plus f of k plus 1 times f of k minus 1, we can choose f of k equals k, for example, and then please derive it by yourself. We get the summation over the inverse tangents of 2 over k squared equals 3 pi over 4. Okay, this is also very nice sum. If we take f of k minus a over k squared plus 1, we get this nice sum. Then of course we can differentiate with respect to a to get this sum. We have seen this at the beginning of the video, and of course you can differentiate again and again and again to get more and more crazy looking identities. So a small summary, and then this was it for the first part. Using the addition theorem for the inverse tangent or for the tangent and the telescoping property, we get some nice sums, and to make them more crazy looking, we differentiate. And what about other crazy sums? So in the next part we discuss, like I said, we discuss not Ramanujan's sum, but we discuss a small brother of it. And we are doing that via, I called it inverse tangent sums via zeros of complex functions. With this tool we will be able to find also really nice summations, and like I said, the Ramanujan sum, here the second one, it's not so trivial or obvious in some sense. This should be an own video, but this one, after understanding where it comes from, we will be able to derive some others. Yes, so see you next time. I hope you enjoyed the video with the inverse tangents. See you next time. Bye bye.